Welcome back to this project on k-means clustering for imagery analysis. In this video, we're going to move on to optimizing and evaluating the clustering algorithm. Furthermore, we are going to be doing some visualizations of these cluster centroids. That is going to be a really cool part of this video, but that's going to come in the second half after we actually optimize this. So let's dive right in. From sklearn, we want to import metrics. We're going to start by defining a function that will calculate several different metrics for us so we can have an idea of how well our k-means clustering algorithm is performing. So we'll define this function, calculate metrics. We'll pass to it the estimator, which is just going to be the k-means here, the data, as well as the labels. We'll add all of this in there. And we'll calculate a couple of these metrics and print them out. So the metrics that we're going to be using, number one, inertia. Inertia is simply a within cluster sum of squares. So it's looking at the spread of the clusters. If we have clusters that are very tightly grouped, we're going to have a lower inertia than if we have clusters that are widely spaced in the high dimensional space that we're working in. So inertia is generally going to go down as we increase the number of clusters. However, it will give us a good way to compare the performance. It's used frequently for that purpose. We're also going to be using the homogeneity score. So a clustering result is going to satisfy homogeneity if all of the clusters contain only data points which are members of a single class. So up above, when we actually had these print statements, maybe let's go ahead and do those one more time. We saw that some of these clusters don't have members of a single class. They have members of multiple classes, so this is going to score poorly on the homogeneity score, whereas some of these clusters are going to do better since they have all of the same classes. So that's what we're looking at. We're going to try to optimize that as well. And then also, of course, we are going to be using accuracy. Since we're using this for classification, accuracy is ultimately what we're going to care about. However, in this calculate metrics function, we're only going to be doing the several clustering metrics, homogeneity, and inertia. So let's print off, number one, the number of clusters. So the number of clusters is what we're going to try to optimize. So it's important to know what results we're looking at. Let's also print off the inertia. So this is really easy. You can access it right from the estimator. So format, or dot format, more appropriately, it's going to be the estimator dot inertia underscore here. There we go. And then finally, let's print off the homogeneity dot format. This is going to be metrics dot homogeneity underscore score labels, and then the estimator dot labels. We'll get past to that as well. So actual class labels, estimator labels. Okay. So let's run this. We haven't called this function yet, so that goes just right away. All right, so let's start optimizing our algorithm. Let's define a couple different numbers of clusters. So this is going to be a list. We're going to do 10. That's the number of digits. That's the low end that we were working with before. Let's kind of bump this up to some nice even numbers. 4 squared, 6 squared, we'll do 36, 64, 144, and then maybe 256 to really hit that high end. So this gives us a nice exponentially increasing range of clusters. All right, and let's test those. So test different numbers of clusters. For number of clusters in clusters, which is that list we just defined, we're going to define our estimator. So estimator, let me scroll down a little here, it's going to equal the mini batch k-means, which we used before, where the number of clusters is going to be equal to number of clusters. and then we're going to fit that estimator straight to the X training data. The normalized and pre-processed training data, that is. Let's go ahead and print cluster metrics. See how we did. So we can just call this function, calculate underscore metrics, estimator, the X data, the Y labels. But we didn't include accuracy in there. So what we want to do is we want to now determine predicted labels using the functions we defined above. So cluster labels is going to equal infer cluster labels, pass to it the estimator and the Y labels. And then we can say predicted Y is going to be equal to infer underscore data underscore labels estimator dot labels underscore comma cluster labels. There we go. So those are the two functions. We'll have our actual predicted integer values. And then we can calculate and print the accuracy for these. So to do that, we simply have print function, accuracy. I'm going to add in a new line character here so that we have some spaces between each of these clusters, or each of these algorithms with a different number of clusters. This is just going to make our print statements look a little bit nicer. So what we want to print is the metrics.accuracy score, and then the actual labels Y, and the predicted labels Y. All right, so there we go. There's that. This accuracy score metric is simply a comparison. How many did we get right? How many did we get wrong? Whereas our metrics up here is going to be our inertia and our homogeneity. So let's see how some of these do. Let's go ahead and run Shift-Enter here. Start running these cells. The first ones are going to go faster. The smaller the number of clusters, the faster this is able to fit it. And again, we're using the mini batch k-means, so it's going pretty quick. Awful accuracy on the start, but we're quickly getting better actually as we increase the number of clusters here. Only a little bit better there, surprisingly, with the number of clusters 64. Our homogeneity score is going up each time, only slightly, from 36 to 64. Substantially here when we go to 144 clusters. We also see that our inertia is decreasing. So the inertia would be a perfect 0 if there was no sum of squared difference between these points in the clusters. That would happen if we set the number of clusters to the number of data points, because there would only be one data point in each cluster. This is pretty high just because there's 60,000 points in these, so it's dependent on the number of data points that you have, but it is decreasing as we go up. All right, and here we go. Our biggest number of clusters, 256, actually got a score of 0.8995, so 90% accuracy on this guy. It also had the highest homogeneity score and the lowest inertia. So it's pretty safe to assume that 256 was the best number of clusters to pick out of these. It also looks like we're getting some decaying results here. Maybe we could add in another one. If we do a nice even 400. So we'll fit these again, even though it'll take a little second. We already saw that the 256 was better, but perhaps if we add in an additional 400 here, we could get slightly better. This, I think, is going to give us some slight errors because our batch size isn't going to be big enough to handle this number of clusters, but I believe it'll fix itself for us. And you see we actually get some different accuracy values here in some of these. And this is because we're randomly initializing where these centroids are starting. And that is actually going to have a dramatic impact on your overall accuracy and the results that you do get. So initialization is important for k-means clustering. So we'll let this run. What we're going to want to do, though, next is test this on the actual testing data set. Remember, the accuracy on the training data set isn't nearly as important as the accuracy on the testing data set, because that is going to tell us how well our algorithm can generalize to new information. And indeed, we did get an error here. So it did 3 times k. It automatically corrected it for us as it's fitting this. 89% accuracy again on that number of clusters, 256. So as this goes, and again, it's taking longer and longer the number of clusters, the more clusters that we have. And it looks like we're getting some exponentially decaying results here. So we got substantially better as we increased. And then even actually, oh, this is the homogeneity score. It looks like we'll be slightly better with the 400, but just barely. So it took substantially longer. However, we're getting marginally better results. So we have exponentially decaying returns here as we decrease the number of, or increase the number of clusters that we are using. All right, but let's go ahead and apply that to the testing data set. So we want to test k-means algorithm on testing data set. So first steps to that would be to convert each image to one-dimensional array. We're actually going to have to process the testing data set in the same way that we processed the training data set before. So we'll have reshape length x underscore test, comma, -1 to make it a one-dimensional array. We can normalize the data to 0 to 1. To do that, simply x underscore test is going to be equal to x underscore test dot as type float divided by 255 with a period to denote a float. Let's initialize and fit k-means algorithm on training data. So we'll reinitialize here. So k-means equals mini batch. K-means number of clusters. Since the 400 actually took a lot longer and really didn't give us better results, this difference could be just simply attributed to how it was initialized. I'm just going to set this to 256 here, since that seems to be a decent number of clusters. It's getting us a pretty good accuracy, and it's also pretty quick and works pretty well. So we'll do k-means.fit. Let's do x here. So fitting our training data, remember just the x is our training data. Cluster labels is going to be equal to infer cluster labels k-means y. So the reason we're retraining this on the x data here is so that we can generate these cluster labels and actually this dictionary for which clusters belong to which integer. And then we'll use that. We'll use it to predict the labels for testing data. So we can do that simply. So testing clusters is going to be equal to the k-means dot predict x test. So this is going to predict which cluster each array in this x test belongs to, or which reshaped image, which cluster it belongs to. And then we're going to calculate our predicted labels using our function we defined above, infer data labels, and we'll use the k-means.predict x test here, which would just be the test clusters. So let's go ahead and just pass that directly. Use test underscore clusters here, and then cluster labels as well, so that dictionary that we defined. Let's come down here and calculate and print accuracy, just like we did before. So we'll have print accuracy. Maybe let's say testing accuracy, so we can differentiate between the two. Dot format metrics dot accuracy underscore score y test predicted labels. All right, there we go. So we're refitting on the training data with 256, our number of clusters here. We're generating that dictionary, which clusters belong to which integer. We're predicting which cluster our testing data belongs to, and then converting that to the actual predicted labels and calculating an accuracy score from that. So let's go ahead and run this. This does have to refit the data, so it's going to have to think for a second here, as well as calculate the accuracy score and the stuff like that. But it shouldn't take too long because, again, we're only using the 256 clusters instead of the much larger 400, which got us only slightly better returns. And here, indeed, we see with the 256 that we get a 0.9011% accuracy, so 90% accuracy on this classification task using this k-means algorithm. And we're actually just as accurate on the testing data set as we are on the training data set. So this is good news because we're not overfitting the data in any way. We can generalize it very well to new data, especially considering we have 10,000 images in our testing data set, so we're generalizing well to those 10,000 images. All right, so there we go. It's been optimized for the number of clusters. We've taken a look at that. A good side project you could potentially do if you wanted to explore this a little bit more is maybe fill in a more detailed list here and run this for an increasing number of clusters and then calculate the accuracy on the testing data set and see at what point does it start to level off. At what point do you hit the number of clusters being too high and the accuracy even start to decrease potentially. That would be something interesting to look at. So it could be surprising initially that actually 256 clusters is better than 10 clusters. I mean, we only have 10 digits, 10 integers. People are all writing 1s, 2s, and 3s, so why do we need so many clusters? Well, actually, what this next step is going to show us, and which we could actually infer if we thought about this a little bit, is that there's multiple ways to, for example, write the number 2. And to the computer, those are going to be drastically different images. As a result, they fit into different clusters better than the same cluster. So we're going to do that, and we're actually going to explore that by visualizing the cluster centroids. So the most representative point within each cluster is called the centroid. If we were dealing with x and y points, the centroid would simply be a point on the graph. However, since we're using arrays of length 784, which we saw above, our centroids are also going to be an array of length 784. They're going to be high dimensional and in that space. So we can reshape this array back into a 28 by 28 pixel image and plot it. And that is going to generate a graph and display the most representative image for each cluster. So that's exactly what we're going to do in this next step. So we're going to visualize cluster centroids. And I think this is actually the coolest part of this project. So let's go ahead and do that. So we want to first initialize and fit the k-means algorithm. We got to do this again, unfortunately. So we have k-means equals mini batch k-means, just as before. Number of clusters, we're going to actually set this smaller, 36, just so that we can actually graph all of the clusters. You could plot 256 clusters if you wanted. However, I'm only going to do 36. Don't really care about accuracy here. We're just kind of looking at what these centroids actually look like. So we're fitting to our training data again. And now we want to record centroid values. To do that, we simply say centroids is going to be equal to the k-means dot cluster centers. So these are automatically stored, again, because this is how we're actually clustering these. This is how k-means algorithms work. They pick a centroid and assign all of the points that are closest to that centroid to that particular cluster, recalculate the centroid, and then iterate over that process again and again until the values aren't changing. So we want to next reshape centroids into images. So this is going to be the reverse process of what we did before, where we flattened it into a one-dimensional array. Now we want to take that one-dimensional array and produce a 28 by 28 image. So we can do that. Centroids, this is a NumPy array, so simply reshape. We have 36 clusters, So that's why we have a length 36 here, and we want 28 by 28. So this is the reverse process of the flattening that produced the 784 length array. We want to put that back into this 28 by 28 image. They're normalized to 0 to 1, so we want to times equal here by 255. And then we also want to say images equals images.asType np uint8. So we want this to go back to being an integer value instead of a float value, which is what it would be right here. All right, let's determine cluster labels. So cluster labels is going to be equal to infer cluster labels k-means underscore y, or comma y, pass our actual labels to it. So there's our dictionary. Now let's create a figure with subplots using matplotlib.pyplot. So this is going to be very similar to what we did up above here when we were plotting out the images in our MNIST data set. Just come down here. We'll have figure axis is going to be equal to plt.subplots. And we want 6 by 6 here since we have 36 of these clusters. Figure size, we can set this ahead of time, 20 by 20. It'll make it look nicer. plt.gray. Let's get some grayscale images here again. All right, loop through subplots and add centroid images. That's what we're doing here today. So for I axis, which is the subplot, in enumerate axis.flat. First things first, let us determine inferred label using the cluster labels dictionary. So we'll say for key value in cluster labels.items. So the key and the value in our dictionary. If I in value, what we want to do is axis.set title inferred label for that particular cluster is going to be .format key from the dictionary. So there's that. Next thing's next. We want to add image to subplot. So axis.matShow images of I, and the images, remember, we generated and reshaped up above here. They're the centroids, or the cluster centers, the most representative image for each cluster. I'll do axis.axis off. Let's not be having tick marks on any of these here. All right, and this is pyplot, so we still need to display the figure. So let's go ahead and do that. We'll have figure.show. This will be the end here. All right, so everything looks good. We're generating those centroids, reshaping them back into images. We are then inferring the actual labels using the dictionary and the convenient functions that we defined up above, making a 6 by 6 subplots. Let's see what this looks like. All right, so this is going to have to run. It is fitting, again, number of clusters 36 though, so it shouldn't take as long. There are some processing steps. All right, and here we go. And wow, this is actually looking pretty amazing. Here's our 36 by 36. We have a lot of images here. It's actually hard to display them all in the same in the same window. See if I can make this bigger here. I can't. But these are actually really interesting. So these are the clusters, the cluster centroids. So this is the most representative image for each cluster. And it's actually really easy to see when we're looking at these why we need a higher number of clusters. Because, for example, these are both ones, inferred label 1, but drastically written at an angle. The computer is going to interpret that as a completely different image. But we also need to understand that those are still going to be 1s. Or, for example, look at this cluster over here, inferred label 2. Yes, indeed, that is a 2. But down here, we also have 2s written in a different way. And these are both going to be 2s, dramatically different images, but both corresponding to clusters of the integer 2. Here, actually right above it and below it, we have that great comparison as well. Some of these, like the inferred label 7, so this is going to be a cluster 7, it looks like we do have some 9s that are being cast into this cluster as well. So we're having some misclassifications there, as well as some of these. The blurrier they are, the more the cluster varies. Inferred label 8, it looks like we might have some 5s into there. Our 5s and the 8s and potentially some 6s are getting mixed up, as well as the 4s. Inferred label 7 here, it looks like, again, we got some 4s. But there we go. Those are actually our cluster centroids. Again, this is only for 36 clusters. So for 256, which ended up being a good number of clusters to use, or even 400, even though it only got slightly more accurate, you would have a lot of different clusters. And they would all have a representative image like this. So it's easy to look at this and kind of understand why different numbers or get numbers in the MNIST dataset get classified into these other clusters by looking at these most representative images. You know, this is something that you couldn't exactly do if you're using a deep learning technique. But at the end of the day, deep neural networks are obtaining ridiculously high accuracy on the MNIST dataset. So if you really did want to do a true classification on an image task like this, you probably should use a deep neural network. But that comes along with the different training restrictions that we've talked about in other projects. All right, so this brings us to the end of this tutorial, K-means clustering for imagery analysis. We went through some different techniques, mainly pre-processing images for clustering. We looked at how you can reshape these arrays into one-dimensional arrays and use a K-means clustering algorithm in a high-dimensional space, which we looked at deploying. We looked at how to use different functions to turn those clusters into actual classifications with the correct integer values. We looked at some different metrics such as inertia and homogeneity to evaluate cluster performance. We then optimized this for a different varying number of clusters. We found that higher, 256 or 400, somewhere in that range is going to be optimal in this different scenario. We tested it, we showed that our algorithm can generalize, and we also visualized the cluster centroids, or the most representative images for each of these clusters. In this particular case, we used 36 clusters so we could display them all. So I hope you learned some valuable lessons about working with clustering algorithms as well as handling high-dimensional data in machine learning tasks, and that you actually found some enjoyment out of going through this as well. I think this is really interesting and really cool to kind of look at how these algorithms are making the decisions that they are making. So use this information and go forward and enjoy developing your own applications and applying this information to other tasks. Thank you very much for listening. Have a great day.